Okay, welcome to what is probably the last video in this series. And in this one, we are going to rotate our points around Euler poles. Okay, so we've loaded in our points from an Excel spreadsheet in the last video. And so now we want to rotate these points around an Euler pole. So you may like to read through the workbook. At the moment, we're working from page 5 onwards. But basically, if I'm quite short with it, if we have a point on the globe which has Cartesian coordinates AX, AY, and AZ, and if we define an Euler pole, which I'm going to call E for Euler, and the points in Cartesian coordinates of the Euler pole are EX, EY, and EZ, well, a rotation of this point A around the Euler pole can be given by this matrix equation, okay? So the unrotated point is called A here. The rotated point is called A prime here with this little dash prime thing here. And this thing R is called the rotation matrix, okay? So in other words, if we have a point on the globe and we want to rotate it about an Euler pole, we have to do a matrix multiplication of this rotation matrix to the point A. And it gives us the new point, the point that's been rotated on the globe, A prime. Okay, so the rotation is described as a 3x3 matrix. This is a little bit of mathematical theory. And this matrix, this rotation matrix, can be defined like so. So remember, EX, EY, and EZ are the Cartesian coordinates of the Euler pole. This large omega here, that is the angle of rotation. Okay, so that we define an Euler pole and we decide how far around that pole we're going to rotate our points. Okay, so this matrix has 9 entries, so it has 3 entries in each of the 3 rows. And so these are just given by fairly simple trigonometric functions. But remember that cosine and sine in Python are always calculated in radians. So we have to be a little bit careful with that. Okay, so let's get going. Let's reopen our code and let's define an Euler pole. Okay, so this is the code we had before. If you recall, we plotted the points. Well, sorry, first we read the points out of the workbook and then we plotted the points. I'm going to get rid of this print because I don't particularly want that there. I'm just going to push the plotting down to the bottom because I'm going to deal with that later. Before I plot anything, I want to define this Euler pole. Okay, and I'm defining this Euler pole to be actually the latitude negative 40.360685 and longitude 175.609987. Some of you may recognize that point on the Earth. Okay, and I want to rotate these points, the points in Australia that are encircling Australia, and I'll rotate them around this Euler pole 180 degrees, okay? So the first thing I need to do is convert this point, this Euler pole, into Cartesian coordinates so that I get my EX, where is it? EX, EY, and EZ. Okay. So if you remember how we do that, well, we can define, we have some measurements in degrees here. So we have our latitude in degrees, negative 40 degrees. We have our longitude in degrees, 175. Lambda E. Okay, so I'm going to define my lambda E, so my radian version of my latitude. So numpy dot degrees to radians of the Euler pole, is the entry in the 0th position of Euler pole. So that's this is position 0. So I'm taking this angle in degrees and converting it to radians, and I'm calling it lambda e. Okay, well I should do the same for the longitude. So what was I calling this? I was calling this phi. Okay, so the longitude in radians is given by the entry in position 1 of Euler pole. This entry here is our longitude, and I'm converting it to radians here. Okay, and then I can write down my Cartesian coordinates of this point. And if you recall from an earlier class, we can calculate this like so. We take the cosine of lambda e, and we multiply that by the cosine of phi e. The y component, we take the cosine again of lambda e, but here we multiply it by the sine, right? Sine of phi e. And then finally, the z component of my Euler pole is numpy dot the sine of lambda e. So it's really easy to make a mistake in this step using a cosine rather than a sine, or a sine rather than a cosine, or just misspelling cosine. So we'll fix that. We also want this angle of rotation, we also want that to be in radians as well. So we better angle of rotation in radians is numpy dig to rad AOR. So now we have the Cartesian coordinates of our Euler pole, and we have the angle we want to rotate through. Okay, coming back to our document now, we need to define this rotation matrix. And if you recall, well, this was the definition of each entry in the rotation matrix. So this is going to take you a little bit of time to type all this out carefully. Okay, so well, I'll start. So the entry in position 1 of the matrix is equal to EX times EX times 1 minus, it was 1 minus, wasn't it? 1 minus cosine of the angle plus cosine of the rotation angle. 1 minus numpy dot cosine of the angle of rotation in radians plus numpy dot cosine of the angle of rotation in radians. Okay, well, this is going to take a little while. R12 is equal to EX times EY times 1 minus numpy dot cosine AOR rad. So it's minus EZ times numpy dot sine AOR rad. 13 equals EX times EZ times 1 minus numpy cosine of angle of rotation rad. There's a lot of typing in this bit. Plus EY times numpy dot sine of the rotation in radians. Okay, so that's our first row actually. The first row, entry 1, entry 2, entry 3. So that corresponds to the first row of this matrix here. Okay. So, well, we better do the others as well. 2, 1, EY times EY. You might like to speed through this if you can speed up the video. Numpy dot cosine AOR rad. CZ times numpy sine AOR rad. R22 equals, I hope I'm not making a mistake here. It's very easy to make a mistake on this step, so please take your time. I'm trying to rush because I'm recording this. Plus numpy dot cosine AOR red. Very good. I should have I'm missing a multiplication in this one, I just noticed. But anyway, R23 is equal to EY times EZ times 1 minus numpy of cosine AOR red minus EX times sine AOR red. And finally, so that's the second row done. Finally, the third row, EZ times EX times 1 minus pi dot red minus EY times numpy dot sine AOR red 2 times EY times 1 minus cosine AOR red numpy dot cosine. I missed a bit here. EX times numpy dot cosine, numpy dot sine rather, AOR red, and R33 equals EZ times EZ times 1 minus numpy dot cosine AOR red plus numpy dot cosine AOR red. Okay, so it takes quite a bit of time to type that all out. You might like to just double check everything that I've done and everything that you've done just to make sure that we've all done it correctly. Okay, so now that I have all these individual entries in this matrix here, I actually want to take all these numbers and form them into this matrix, okay? So I have all these individual numbers and I want to make them into a matrix. And the way I can do that in Python is the rotation matrix. I'm going to call rot m is equal to, okay, so I've got, you see, one set of square brackets. I'm going to actually add 3 sets of square brackets separated by commas. Okay, so each of these square brackets represents a row. Okay, so while the outer square brackets represent the whole matrix, each of these inner square brackets represents a row. So here I'm going to put R11, R12, and R13. So this is row 1, R21, R22, R23. So now this is row 2. And R31, R32, R33 gives me row 3. Fantastic. Okay, so now I have my rotation matrix. Now all I have to do is multiply the point, every point. I have to convert every point to a Cartesian coordinate and then multiply that rotation matrix by this vector, this Cartesian point vector. Okay. Okay, so I'm going to iterate over the points. Okay. And I'm also going to create an empty array for the rotated points. So here I have new latitudes, which is going to represent my rotated points, or my A primes, and longitudes as well. Okay. Okay, so I'm going to iterate over all the points in my Excel spreadsheet. So for I in range 0 to the length of A latitude, where if you recall A lat is the array that we stored all the Excel latitude data in. Okay, so for I in this range, the first thing I'm going to do is I'm going to convert these latitudes and these longitudes into radians. So numpy lambda a equals numpy dot deg to rad of a lat I. And then similarly, phi a equals numpy dot deg to rad of a long I just like this for some reason. It's okay. Lambda A, lambda B. Okay, and then I can convert my, in the same way over here, I can convert my each coordinate in A to Cartesian coordinate frame. Okay, so I don't want to call it E, I want to call it A this time. So phi A, lambda A, lambda A, lambda A, A. Okay, and now I want to, I can do this matrix multiplication. Okay, so I've got my Euler pole to create my rotation matrix, and now I have my Cartesian coordinate points. So now I can actually rotate this thing. So A prime is equal to, okay, so using NumPy, this command called matmul is matrix multiplication. So the matrix multiplication we see here, the command is matmul. This matrix times this vector, matmul. Okay, so matmul of the rot m rotation matrix, and now we need to make this vector, right? So again, I'm going to put in square brackets, 3 inner, lots of square brackets, and here I'll have ax, ay, and az. Okay, so this is going to take this rotation matrix and multiply it to this vector of components ax, ay, and az.